Alright, so for this lab, we're going to collect data on the simple pendulum and then the physical pendulum. And we're going to enter the data into this spreadsheet, which is titled Pendulums Data. This spreadsheet is updated now on the Moodle page in the Pendulums Lab folder, or the link for the Pendulums Lab. Now, I've already downloaded all the data for the Pendulums Lab. If you go on here and you click the link for the Pendulums Lab, you'll see all of the files here that you need. All of the files that you have will be right here. So the Pendulums Data Excel file is right here. And then all of the clips for the physical pendulum and the simple pendulum. And then there's two other images, this length scale image and the physical pendulum image. So we'll see how we use all of these things in the lab. Alright, so I put this information all in one folder, the pendulum data folder, so I'll open that up, make it a little bit more compact. So I have everything in here, and the first thing I want to do is look at the theory curve here for the physical pendulum. So the blue line here is the theoretical curve. I've got some values for different lengths, so going from 0.01 meters all the way down to 1 meter. And then this next column calculates what the frequency should be according to the theoretical formula, and then I plot it over here as a nice smooth curve. So you know what the basic shape of the curve should be. It's frequency versus length of the simple pendulum. So the longer the pendulum gets, the smaller the frequency. So longer pendulum swings slower. Now, the data that we collect is going to go in here. So in order to collect data, I need to put this information, or put the video into Tracker. So I've opened Tracker, and I'm going to start with the simple pendulum, and we'll just take simple 1. And we'll do one of each so you can see how the data collection works for both the simple pendulum and the physical pendulum. There's a little bit of difference between the two. All right, so the error message with frame to exclude, that comes up for all of them. Just click OK, and you'll need to rotate the image to get it to look right. Okay, so here we have the string with a golf ball in the end, and the video shows one oscillation. Now we're going to need the length of the pendulum, so the first thing to enter in here is the length of the pendulum, which would be the length of the string down to the middle of the ball. But for that we'll need a length scale, and I measured from here where the pendulum is suspended down to this quarter. So I put a quarter on the floor so there'd be a nice marker that hangs directly below or sits directly below where the pendulum is going to swing. So I know what this distance is, and I took a picture of it, and that's the length scale picture. So when this opens up, you're going to see a picture showing you can't see the bottom of the meter stick, but that doesn't matter. You can see that it's ending here at, if you go to the middle of the axis here, this is where the pendulum's going to hang. That's 89 centimeters, or 0.89 meters. The bottom of the meter stick is resting on the quarter. Okay, so 89 centimeters, or 0.89 meters. That's the number we need to remember. So this button here is for the calibration stick. We go here, calibration stick, and then remember it's shift and click. So one end was on the quarter, one end was up here, and that calibration was 0.89 meters. All right, so now I'm calibrated. I can adjust this a little bit in a second. But what I want to know is the length of the pendulum. And that's a tool we haven't used yet, but it's in the same place as the calibration stick. There's a calibration tape. like a tape measure. And you use it the same way, shift and click. So I want to click on the middle of the ball and then up here where it's hanging from. And so it tells me that's 0.709 meters, or at least that's what it is right now before I do the adjustments. So let me zoom in, and I will put that right on the middle of the axis where it's swinging from, because that's where I measured to in the picture. And I can move this around as well. Now this is where the rope is going to swing. Now the way that I tied it on, it sort of wraps around and then comes down on this side. So I'm going to have this hanging from the bottom of where it hangs down here. So I'm not going to go up here to the center. I'm going to go down here to where it hangs, because that's where it's swinging. So imagine the rope swinging back and forth. It's going to kind of a little bit wrap around that axis. So it's only the part that's swinging that matters. So I'll center it right around there. Then if we scroll down to the bottom where the quarter is, I can center this a little bit better on the quarter. Okay, scroll back out, and let's look at the ball, make sure that we're kind of at the center of the ball. Okay, around here. All right, so where are we for a length? 0.710 meters. That's the length measurement. 0.710 meters. Now I've changed my notation a little bit, so I'm just putting sigma for the uncertainty or the error in whatever quantity we're measuring. So this is the length in meters. Here I want the uncertainty in length in meters. Now with the uncertainty in this, really there's just a little wiggle room where the where does it start and where does it end. I think to be safe on this, what you can say is the uncertainty is sort of like about the radius of the ball. So if it's here, it's 0.71. If I go down here, it goes to about 0.73. So I think the safe error is right around 0.02. That seems to be reasonable. Now it's probably a little bit less than that, but just to be on the safe side, let's say 0.02. Okay, now that would be the same for all of them, essentially. I'm taking each video from the same perspective. The ball is going to be about the same size. And so we can just drag that down and keep the uncertainty the same for all of them. All right. So I've got the length. Now to get frequency, I need the time it takes to make one oscillation. And the spreadsheet will then calculate the frequency. Frequency is 1 over the period. Okay. But to get the period, what I will do is use the time stamps on the frames. So if you come down here to the bottom left, it counts frame number. But if you click that button, you can change the display to time. So I changed it. Now this will be the time. And I can step forward with the video until I get to kind of the max. And you know you're at the max when the next image you click decreases the amplitude of the swing. So if I go back 1, okay. So it looks like the beginning of my swing is right here. That occurs at a time of 0.195 seconds. So my first time is 0.195 seconds. Then I'll hit play. We can watch it swing in slow motion. You don't actually have to watch it. You could just click it forward, but let's watch it swing. It'll go to a maximum on this side, and then it will swing back down to here. On yours, this should actually go a little bit quicker. While I'm recording a video and playing this video, it really slows things down a little bit. Okay, when I get close, I'm going to pause it. and then I'll step one by one. Okay, so that looked like it came back, so I'll go back one. 1.897. So I'll put in 1.897 here. Then the time I can calculate. So what is that? Wait, what happened? I thought it was 1.897. Let me check this again. Okay, that's going down. It's going up. 1.863. All right, and then I want to calculate the period here. The period is the difference between those two times. So I can make this a formula equals this minus this. And that formula will be the same for each trial, so I can drag the formula down. Now what about the uncertainty in the time? Well, my limitation in the video is a frame. So what I really need to know is, what is the time for a frame? So I'm at 1.863 right here. What if I go back one frame? Oh, that'll go back all the way. Let me go back one frame. Okay, it goes to 1.830. So the difference between those is the time that it takes in between frames, which is 0.033. So that's a safe bet for the uncertainty, 0.033. Too many zeros. Let me 0.033. All right. So the data looks good. It's right on the curve where I expect it to be. Okay, the error bars should show up automatically. The error bars for frequency are pretty small. That's why you can't see them for this point. The error bars for length are a little bit larger. Those are over here. And we have one data point completed. Now to do the next one, you just do that work all over again. So you don't need to save anything here. You can save it if you want to come back to it, so you can save the file, but I'm not going to. I just close this tab. I'm not going to save any changes. Open a new tab, and then once the new tab is there, I upload a new video, do it all again. Okay, and fill this all out for the simple pendulum. But let's skip ahead to the physical pendulum. All right, so for the physical pendulum, the theory is here, and you'll notice it's not showing you anything yet at the beginning, and that's because I haven't put in data for this number right here, the length of the physical pendulum. So I took a picture of the physical pendulum with the meter stick right here so we can see the length of the physical pendulum. So let's zoom way in and go to the top. And you can see here the physical pendulum is a length of just about 60.5 centimeters, or 0.605. So that's the length of my pendulum, and when I put this number in, the theory will update. Okay, so this is the curve that you expect. This is where you expect your data to fall. Now the x-axis here is the little l divided by big L. Big L is the full length of the pendulum. Little l, which you'll have to put in for each one, you can get off this picture. So little l is the distance from the bottom of the pendulum to the hole. Okay, so for instance, the first hole, this one, is right here, and if I go, I'm trying to go to the middle of the hole, that's right around here. That looks to be like 32.9 centimeters. So I'll put that in as 0.329 centimeters. Now what about the uncertainty in these two values? Well, my ability to read the meter stick here is limited by the quality of the image a little bit. But let's think about like how big are the openings here that we're trying to measure, and how do they compare to the tick marks over here. So I say the center is here at this one. I think it's probably safe to assume that it's as high as up here and as low as up here. So it seems reasonable to me that you could be off by 1 millimeter on either side. Right? And the same thing could be true here at the end. You could be off by 1 millimeter to either side. That's sort of where the uncertainty lies, your ability just to read the meter stick. So I'll put in for these uncertainties 0.001, 0.001, and again, they'll be the same for each one. So use this picture to get these lengths. And I'm not going to do any more of them right now, so I can close this. But you'll need to go through and find the center of each hole and match it up with the length. What I need to do is get the time it takes for one oscillation. So I need to fill in the data the same way I did as the simple pendulum. The physical pendulum actually goes a little bit quicker because you don't need to do a calibration to get the length. We get the length from that one picture. So what you need to do is upload the video and then measure the time. And the calibration doesn't have to happen. Okay, so same error message, click that OK. Let's rotate it. Okay. And again, we're going to step through it to see where we reach our peak. So it's still moving up. Looked like it came back down in that one. Okay, so let's try that again. Okay, yeah, looks like the second frame for this one is where it's at its maximum. I can make this a time, and that occurs at 0.123. So my first time is 0.123. Where's the second time? So maybe I'll skip this one ahead a little faster. Okay, and I'll step it forward frame by frame. Okay, looks like that one, it came back. Yeah. So it looks like right here we're at the peak, the biggest angle, 2.258. And again, we calculate the difference, so equals this one minus this one. That's the period, 2.135 seconds. The dot pops up right where you'd expect it to. That formula will be the same for each one. And my sigma, my uncertainty in this time, is really the same as it was before. It's the length of one frame. That won't have changed because I used the same video camera. This time between frames will be the same, so this will still be 0.033. And again, same for everything. Okay, so just like with the simple pendulum, you repeat those steps each time. Get the length from the picture, upload the video, change this over to time, and then find the frame where it's at its maximum, or right like when it's reached its peak over on the right hand side, and then play the video until it returns back to that same point, mark the time again, and then everything should update here. And you'll get a nice smooth curve. Just to show you what your data should look like in the end, I went through all of the images and collected it so you have something to compare to. It should come out pretty nicely if you do this right. So your simple pendulum data should look pretty close to the curve, and so should the physical pendulum data. This is an experiment where the numbers work out really nicely. Okay, and that's pretty much what there is to this lab. It's collecting the data, and then you can edit these graphs if you want to make them a little bit more personalized, however you want to. But the main outcome of the lab is getting the data to look pretty close to the theoretical curves, what you should expect to find. All right, I think that's it, and I will stop the video there.